Okay, we want to apply this idea now. And we're going to start by applying it to nonlinear elasticity. But we are going to apply it to a general situation where we don't have just a ball, which is a rigid object, but we have a deformable body viewed either in the reference or in the current configuration. All right, so that's the setting. Okay. We are going to extend this idea or I should say these ideas to elastic, which means of course deformable bodies. Okay. And in particular, of those few examples I put up a couple of slides ago, we are going to study the case of what it means for a body to be in elastic equilibrium, right, or mechanical equilibrium. Okay. All right. So what this means then, if this is what we want to do, you observe that that argument that we sort of sketched out in the previous slide was in terms of energy. So we need to define some such energy here. Okay, and in particular, we need to define an energy that is applicable to the body to the whole body, right? Okay, whether it's here or in its current configuration. Okay, so the goal here, where we need to start really, is to first define a suitable energy. Okay, right, just in the context of elasticity. Define a suitable, so let me say that, define a suitable energy for an elastic body. Right, non-linearly elastic. Now, we already know about an energy, right? We've used it very often in our study of nonlinear elasticity. In fact, after a point, our study of nonlinear elasticity pretty much revolved around this notion of an energy. Okay, you recall that we have the strain energy density. Okay, psi, and in general written as a function of f. Of course, we know things beyond this, right? Though I'm writing it as a function of f, we know that all our, our fundamental requirement of material frame invariance holds, right? So though I'm writing it as a function of f, we know that it's a special function of f, and we know how to write all that special aspect of it, right? So let's assume that all of that holds. Okay. All right. Now, so we could go ahead and write this as psi, which is okay. Just for the moment, I'm going to write f as isotropic tensor plus displacement gradient. Okay. Now, we may look at that in the reference configuration or the current configuration, right? We may consider it in either setting. We know that f goes between the reference and current configurations. Okay, but you note that since we're talking about this, since what we've written here is the strain energy density, we are really talking about the energy per unit volume in some little neighborhood of our position, either in the reference configuration or the current configuration. Okay, when we consider psi, it does not give us the total energy of the body. Okay? Now, of course, you've probably seen how to get around that minor impediment. You may say, well, that's no problem. We just integrate it over the body, right? We get the total strain energy, and that's right. Okay? So, to get total strain energy, integrate, right, over omega naught. Okay? In particular, you may say, well, let's just do that, right? You may say integral over omega naught, psi function of f, d capital V, right? That gives us the total strain energy. Right. Now, it turns out that when elastic bodies are at equilibrium, they are at equilibrium or not, depending not just on the strain energy, but also on the forces applied to the body. In particular, if we have a traction boundary, right, we know that there is a traction vector. Okay? And in the current configuration, we would have this. Okay, and we know that that traction vector is fixed, right? Okay, right. Or actually, sorry, capital T here would have to denote the total force, right? So that's the total force on that area vector. Okay, and this would also have to write here that this is the force on little n dA, right? And we've studied about the implications of all this. So it turns out that we need to include that effect. Not only that, but we also need to include the fact that there is a body force. Okay? There is a body force which in the current configuration we've denoted as Bf, and in the reference configuration we've seen that this is just the Jacobian of the deformation, right, or the determinant of the deformation gradient times Bf. So bodies are at equilibrium or not, if they are elastic bodies, depending upon the traction applied to their surfaces as well as the body force, right, the effect of the forcing. Okay, it sort of makes sense. I mean, how can we talk about the equilibrium of a body if we don't account for the fact that there are forces acting on it, or that there are internal body forces, right, like gravity, right? How can we talk about equilibrium without accounting for those? Okay, so we need to account for them. Sorry. In order to get that right, what we need to do is include essentially the work of external forces. Okay? So what that lets us do is, what that means is that we need to integrate over omega naught, not just psi function of f dV, okay, but we also need to include the effect of the work. Okay, so the work done is integral over omega naught, the work done by the body force is that, where u is the displacement. Okay, and I have j Bf because I'm talking of things in the reference configuration, minus integral over the traction boundary of T dot n dA, okay, where T is now the traction vector. All right. Now, because we know that that F here is written as isotropic tensor plus partial derivative of u with respect to x, what we observe is that this energy that we've written on the right-hand side is dependent on the displacement field u. I'm going to use the same symbol pi for it as we did before. Okay? There are some things I need to say about this energy we've written. Let me say that in a few remarks. Okay. What we've written here is another version of a thermodynamic potential. We first saw a thermodynamic potential, the Helmholtz potential, when we studied thermomechanics. Okay? This is a thermodynamic potential called the Gibbs potential. Okay. Also, just like the Helmholtz potential, it's often called the Gibbs free energy. Okay. The other thing you note is that this gives us the energy in the body, but mathematically speaking, this object that we've written pi, depending upon u, is not a function. Okay? It is a functional. Okay? And the difference between a function and a functional is that whereas for a function, you could work with, a function, say f of x, right? How does a function work? It takes a point value of x. It says, okay, you give me an x, you give it a value of x, and it gives you back the value of f, right? So you may say, if that is x here, then that is the value of f I get, okay? And maybe your function was that, okay? A functional is different, okay? In 1D, it is as if you need to know, in 1D or maybe, or in 3D, or even in 3 dimensions, right? In 3 dimensions, a functional is an object to know which you need to know an entire function u, okay? All right? So a functional, pi is a functional of u, okay, where u, in this case we know that u is it can be a function of little x in time, right? U itself is a function, okay? What this means is that to evaluate the functional pi, it is not enough to just have a point value of its argument, like we have in this case, in the case of a function, okay? Whereas in this case, we have a function f of x. This is very different. Pi is a very different object, okay? For pi, in order to evaluate pi, you need to know the entire function defined over the entire domain, okay? What this means is that to evaluate pi, we need u defined over all of omega naught, right? And maybe omega naught cross the interval 0 to t, right? If you're interested in time as well. Okay, so u is a mapping from omega naught cross the time interval, okay? And what we're doing is to draw its arguments from here, right? X comes from omega naught, little t comes from the time interval 0 to t. So u is a mapping from those spaces into the space of, into three-dimensional space, right? Into R3, because u is a vector, okay? Now, it is common to recognize that the function u may have certain mathematical properties, right? Like by mathematical properties, it may be something as simple as saying, well, maybe u is polynomials, or it's exponential functions, or harmonic functions, or something else, okay? So what we will often also do is to say that u belongs to S, right? Where S is what we think of what we mean by S is that it represents a function space. Okay? Example, polynomials. Polynomials in position. Okay? All right, and we know how we get this, right? This works, right? This idea works because we already think of u as depending upon position, right? So what this says is that, well, maybe we want to just think about u as depending, having some polynomial dependence upon position, okay? This is what gives us the idea of a function space. This means now that u can be written as polynomials in X, right? Or maybe, like I said, maybe other functions, right? Exponentials or trigonometric functions or whatever. Okay, so this is an idea we will often use. In this sense, the functional pi is a mapping from the space S into another space. Now, what kind of space does pi map into? What are the values that you get for pi finally? Remember, pi is an energy, okay? Or a thermodynamic potential, right? Which is a scalar, okay? So pi is a mapping from our function space S into R, okay? All right? So we have this idea of a functional that we've denoted as pi. I made the point that it is, in a broader sense, understood as a thermodynamic potential. It's called the Gibbs potential or the Gibbs free energy. And we also made the point that unlike a function, to know pi, we need to know an entire function itself. Okay? Right? It's not like we could just have a point value of its argument and thereby evaluate pi. No. We need to know its argument over the entire domain, right? Over the entire domain. Okay, so this is a fundamentally different type of mathematical object. When we come back in the next segment, we are going to understand what it means to take derivatives of this type of an object. Okay, so a thought that I'm going to leave you with is, how do we define a derivative of pi with respect, WRT for with respect to u. Note that this is not simple, right? Because you need to talk about we need to talk about what it means to take a derivative with respect to an entire function. Okay? So, all right, when we come back, we will try to understand this question a little better and try to define this idea of a derivative.